Welcome to our webinar on measurement system analysis. We will be utilizing Slido today, so feel free to pull out your mobile device, scan the QR code. We will present it again later as we get to those screens with the questions. We have three presenters this morning: myself, Marnie Ham, consulting engineer at GE Aerospace; Anna Delano, principal engineer at GE Aerospace; and Justin Kraus, lead engineer at GE Aerospace. All right, we're going to start with thank you for coming. We're going to go through some basics of what we do for all our SMIGs. Then we'll have Anna jump in talking about explaining what an MSA is, the importance, the impacts, the process, the different types. And Justin's going to jump in there around the types, or MSA versus Gage R&R. Then we'll close, and there are multiple members of the 13003 SMIG team here as well who may jump in for the question and answers, and then we'll summarize and conclude. Thank you. All right, next one. Today's presentation is recorded, so that you know that. It will be posted on the AESQ website, usually within a couple days of the webinar happening, sometime sooner. So that way you can refer to it or send other people to it. We will have question and answers during the end of the presentation, so we do ask you to wait to the end, and we do ask everyone remain on mute while the presentation is going on, just to avoid that background noise, and especially because these are recorded and archived for future use, we just like that nice quiet time during the presentation. Then absolutely open up your lines to ask questions at the end. RM 13003, or the Measurement System Analysis, RM, is created by a SMIG, or Special Members Interest Group, all about measurement systems. We provide input directly to AS 13100 in the clauses related to MSAs, measurement system analysis. We generate the gold book, shown in the bottom right corner. That's the reference manual on how to do all this stuff. And we meet every other week, sort of preparing, talking about what we need to do, whether it's against the RM, the standard, or creating webinars or resource material. So we are all volunteers from different member companies. So our SMIG, as I said, we are preparing content for AS 13100. We prepare the RM material content. We do communications. We have a LinkedIn site. We create training, webinars, syllabi, and have a community of practice through LinkedIn. So we're all specialists within measurement system analysis for various companies. We compare, collaborate, and try to come to consensus on what would be useful through the whole supply chain. So that's what we do on a regular basis. Our goal is to ensure that AS 13100 is current, relevant for people. The RM supports use of AS 13100 and gives good context to how to use it as well. We support members who are trying to apply 13003, so we will answer questions. And our goal is to increase knowledge in the area of MSA and further develop techniques. So the RM is not going to be stagnant, it is evolving. And one of the things we're trying to do is incorporate more techniques in it than we have already to give more resources and more ability to work together on this. Our RM SMIG group is unique in that we have a very strong collaboration with IAQG and the Supply Chain Material Handling book, trying to both coordinate efforts between the AESQ reference material and the Supply Chain Material Handling book so that they don't have conflicting material in them. This is a list of members that we currently have for RM 13003. I'm Marnie Ham, I'm the deputy chair, and you can see we have a good mix of people. Although this webinar is very GE Aerospace, we decided to collaborate together to do this one. We have members from across the world and many companies. All right, our community of practice. This is our LinkedIn group. Please join. The code is at the bottom there. We will answer some basic questions there or point people to the webinars. We get ideas for what next webinars might be through the LinkedIn site, but it's a great place to connect with other people who are interested in MSA through different companies throughout the aerospace area, especially within engines. So we try to post something on a regular basis But it's always great when other people can give us ideas too. And it gives us ideas of tools and support that's needed. All right.
Hello. So our goal today is that by the end of the webinar, you will be able to explain what measurement system analysis is, while also understanding how important it is to conduct MSAs, how important it is to analyze the results of your MSA, and especially add on those results. Okay, so we're gonna try to make you understand how not conducting an MSA is going to affect your decision. In the sense that you might make decisions you will not be happy with later. After the webinar, you will be able to outline the MSA process, discuss the type of MSA, and you will be able to select the type of MSA more appropriate for your data. And very important, you will be able to tell the difference between MSA and Gage R&R if they're different. Okay, so next slide, please. We're going to start with the Slido question. Okay, so get your Slido and let us know, have you heard about Gage R&R? Great, we have 100%. So let's go to the next question then. Okay, the next question is, have you heard about MSA? Let's answer that too. We go to the next question. Okay, are Gage R&R and MSA the same thing? We have two less answers than in the previous questions. But okay, let's go and start by what is MSA. So a measurement system is not just a tool that you're using to measure or to inspect an item. It is a set of hardware, software, the people, the methods that you're using, the environmental conditions in which you're getting the measurements or you're inspecting something, right? So every element part of the measurement system might affect the measurement system. And MSA is the process that we use to assess all the sources of variation and uncertainty in the measurement system. And it is a statistically based process. Okay, so you can see, like, for example, when you have the policeman taking a measurement of how fast you're going, it's not just the radar gun that is the measurement system, it's the location, it's the car, it's the environment that when the measurement is taken, okay? And so all those elements of the measurement system might affect how how the measurement system is. Next slide, please. So now we're going to look at how is MSA important. Okay, we use measurement data in every phase of the development and manufacturing process in the aerospace industry and also in other industries too. So we made decisions that are based on these measurements, since the measurements are used to accept or reject our products. So MSA provides the verification to trust the measurements that we taken. And it also validates the measurement system as the right system for the specific characteristics that you're measuring. So it is the key that it is very, very important that we add on the results of the MSA, not just do the MSA, do the analysis of the data that you have collected, and of course, add on those results. So we need a valid MSA. Without a passing MSA to validate the measurement system, we can make wrong conclusions with respect to our processes, our products, etc. And also we can take wrong actions. Okay, so we can be sending our customers non-conforming parts, or we could be scrapping good parts. We don't want to be in the situation that we see on the picture. We passed the test, yeah, but then why is not fitting where it's supposed to be, that part, right? So that's why we need to do MSAs. Next slide, please. So we're going to take a look at a couple examples. The first one, and we're doing a manufacturing inspection. We have to ship a part. The decision to ship the part or not to ship the part is made based on that measurement. How can you trust a measurement if you don't have a passing MSA? It might happen what you see in the picture. Somebody measures 30, somebody measures 31. So what do you do? Do you send it to the customer or you don't send it to the customer? So another example is in design of experiments. So you're going to have a number of factors, for example, pressure, temperature, altitude, etc. How can you trust setting the right levels of temperature, for example, to perform your MSA? If you don't have, if you don't have a passing MSA, you might not be able to set the temperature at the levels that you want. And if you cannot do that, how are you going to rely on the results? And how are you going to make any conclusions if you cannot trust your measurements? Okay, so by improving measurement inspection capabilities, what MSA is going to do is enhance yield and reduce scrap. It's going to reduce the false fails, mitigating producer risks, and it's going to also reduce false effect, which are going to minimize consumer risks and product risks. Okay, and if you think about it, MSA ultimately increases our customers' confidence in the quality and reliability of our products. Okay, so next slide, please. So process control, we can use the measurement system to measure, for example, a characteristic. But we have this example later. Can you go to the next slide too, please? Okay. So let's look at the MSA flow before we go to that next example. There are several types of MSA, right? So the types of MSA is going to depend on the kind of data that you're collecting. So here's basically a representation of the flow and the logic that is going to help you to decide what type of MSA you need to perform. So is the data, the first question is your data, the data that you have collected is continuous or it is discrete? If it's discrete, are you looking at the number of defects per part, or you're looking at is the part defective or not? If you're looking at the number of defects per part, you're going to do an intercorrelation study. If you're looking at is the part defective or is not, then you perform an attribute agreement study. So on the other hand, if your data is continuous, you're going to question, is the data, is the data computer generated, or and in that case, you will follow the computer-driven measurement system study, or it is not. If it's not computer generated, then you follow this other side, which will be you'll do a resolution and an accuracy ratio, a bias study, and then a Taiwan study, or you would do the Gage R&R, or you would select the computer-driven measurement system study. Okay, so in the continuous side, you will do the resolution, accuracy ratio, and bias study, and then you will go to the computer-driven measurement system if you have to. Next slide, please. So we mentioned before that the MSA is the process that we use to assess the sources of variation and uncertainty in the measurement system. So let's talk about the characteristics of the measurement system. Measurement system should be accurate and precise, right? So accuracy is determined by 4 different characteristics, resolution, bias, linearity, and stability. So the resolution, and we'll see more details later, can be defined as the ability to discriminate between measurements. For example, and then the bias is the difference between the true and the measurement value. Linearity is basically defined as the absence of bias across the range of the system. And stability is the consistency. And then with respect to precision, there are two characteristics that define the precision of a measurement system. These are repeatability and reproducibility. So the repeatability is the variation in repeated measurements by the same operator using the same gauge in the same location and the same parts. And the reproducibility is the variation in repeated measurements by different operators using the same gauge, location, and same parts, okay? So basically the takeaway of this is that the goal of MSA is to understand and quantify the sources of measurement system variation, okay? Next slide, please. So here's a more graphical definition of resolution in a measurement system. So it's, the resolution, we can define it as the incremental ability of a measurement system to discriminate between measurements, right? So for example, if you're going to measure something which the tolerance is plus minus 0.01, your gauge should at least be able to measure one more digit. Okay, so it should be 0.001 instead of just 0.01. Okay, so for example, if you're going to measure something in that is 5 centimeters, and you use a ruler that can only measure inches, you're not going to be doing a good job on the measurement system. Okay, you need a different measurement system for that. Next slide, please. So here's the example that was on the other slide that I thought it was better in this one. So we have an instrument that can only measure 2 digits. The lower and the upper are the lower and the upper specification limits are 2.45 and 265. So you can see on the left side of the slide the actual measurement, and we're at tool, our low resolution tool that can only measure 2 digits, what it will measure. We mark in blue the ones that are going to be a problem, right? So when we do an IMR chart, you see it there. It might not be very, because of how the measurements are, it's not very clear, but we augmented a part of that picture on the second side, which has the actual measurements, not the measurements provided by our low resolution tool. And you can see that we are kind of like accepting parts that are not really within the specification limit, okay? So one other thing I want to mention here is sometimes it's easy to determine if your measurement system has enough resolution by plotting your data. And this plots is not very, very clear, but sometimes when you look at for example, an IMR chart, control chart, and you see like the data looks more discrete, even though it's continuous. So you have like for example, here, you're measuring the same thing with 3 of them, right? But if you look at the measurements here are 652, 2.652, 2.655, 2.651. Why are we measuring the same thing if they're different? Because our our measurement system doesn't have enough resolution, okay? So also, when we're having, using a control chart, the measurement system should have been evaluated and be reliable to really trust what we're doing in our control charts, okay? So please, next slide, please. Let me know if you think I'm going fast, okay? So here is an example of bias. We mentioned that it's the difference between the true and the measured value. So you can see that in the top plot, all the measurements are really around the ball size, right? While in the plot below, they're centered on the side. So we see some bias on the second, on the lower part, right? We're measuring around a specific measurement, but it's not really the true value. It's not in the bullseye, okay? So that's our system in the second case has some bias. Next slide, please. So stability, as defined before, is the consistency of the measurement system over time, right? So a measure of how variation in accuracy changes over time and with the environmental factors, for example. Okay. So next slide, please. Repeatability. So it's a variation between the measurements of the same part, but the same person using the same instrument. So the plot on the left, the operator is measuring the same part several times, and the measurement system seems to not be repeatable. While on the right side, the measurement system is repeatable. So all the measurements are really close together. We're measuring around about the same thing for the same part with the same operator. Okay. So in the next slide, please. We're going to see so this is the reproducibility. So in this case, we're using different operators to measure the same part. Okay, and we can see on the left that the different operators cannot really repeat the measurements of the other operators, but on the right side of the plot, we can see that all of them are more or less the same, right? So, and now we're going to have Justin continue with the MSA process. Justin?
Awesome. Thanks, Anna. So this next section is going to be going over the continuous data MSA process. As you can see in the figure that Anna talked about earlier, so we're going down the left side of the figure. So step one, the most important part of any MSA is planning of it, making sure your operators are skilled, the gauge is the correct gauge, as Anna was stating earlier, the part variation that you need to conduct the study, and there's quite a few more other factors that go into that. But planning is definitely the most important part. Item 2 is the resolution study, which Anna went over. Step 3 would then be the bias study. Step 4 is the type 1 gauge R&R, which is one operator measuring the same part multiple times to ensure that the gauge is repeatable while removing the variation from other operators. And step 5 then is a type 2 study, also known as a gauge R&R. So during the gauge R&R, it's broken down into a few main steps here: selecting and identifying the parts used in the study, identifying your operators, identifying the inspection and measurement location and environment. As stated before, the environment is still a portion of your MSA tool, right? It can strongly affect temperature, pressure, all of that can strongly affect measurements. So knowing what that production environment will look like and trying to mimic that as closely as possible will reduce variation. The fourth one is verifying the calibration of gauges, making sure that they're fully functional and measuring correctly to calibration standards. The fifth step, determining the measurement order and measurement of parts, and measuring the parts, sorry. So ideally, you want a random measurement order so the operators can't in their mind remember values and start assigning values to their head or deciding, oh, I should maybe remeasure a part. That's not a part of the MSA process. We're trying to see that true variation in the measurement system. And the final step is collecting and analyzing data. All right, next slide, please. So on the left, we have an output figure from the Minitab Analyzing Assistant. So I'll walk you through this really quick. The chart in the upper left is the gauge compared to process performance. So as Anna talked about earlier, gauges can assess a process and gauges can assess product. So this upper chart is showing that you have 90.5% of the process variation is being taken up by the gauge itself. So you really can't properly assess or have confidence in your assessment of a process performance based on this gauge result. Looking at the middle portion of the chart, so can you sort good parts from bad? So this is an analysis of the product. So can you determine good product from bad product? As you can see, the value here is 0.5% based on this example, showing that the gauge measurement system variation is only taking up a 0.5% of the total tolerance, which shows a high capability of measuring good parts from bad parts. Next slide, please. On the left, we have another output from Minitab, which is a statistical software. These are charts that are commonly used across multiple types of statistical analysis for MSAs. All of these are showing a different type of variation in a pictorial form. So in the upper left, it's showing how operators, so the blue operator and the red operator, differ when they measure each part. So you have your measurements on the y-axis and your parts on the x-axis. And as you can see on part 18196, which is the first one, the operators are fairly close together. The second part, there appears to be a large difference, as well as the third part. And you can continue that analysis throughout the chart. The bottom left is just comparing the overall measurement variation in a box and whiskers plot. So you can see it appears currently that the blue operator has higher variance compared to the red operator. That may be something that we need to look into, even though we have a passing value for product, determining if it's passing or failing. All right, so this chart on the right here is from AS 13100, table 4. These are the high-level values that are used for measurement system characterization of whether you can have confidence in the measurement system or not. So as you can see, there's, for all the different studies that Anna went through, there are a percent to tolerance or a ratio given for the different characteristics types, critical, major, or minor. And we've highlighted the Gage R&R row because I'll be using this in the next slides for some examples. And we're going to assume in the next slides that the characteristic is a minor, so less than 30% of the tolerance will be acceptable in that situation. Oh, sorry. So that data was actually used earlier in the slides. That less than 30% was what we were using the Minitab analysis. I got a little mixed up on the slide order there. So comparing that less than 30% to the the 90% for the process and the 0.5% for the product disposition, that's how we got the passing and failing on those. So that was for continuous data. This next section is for discrete data. So if the inspector is determining pass fail, or there's different levels of a defect, so rated 1 through 5. So we're binning the results of the inspection. So again, The most important part of the MSA is planning it out, ensuring that every portion of the MSA is thought about to reduce the variation outside of the measurement system itself, like the gauge, the environment, or inside of the measurement system. So the operators, the gauge, and so forth. With an attribute agreement, which is the right side of the upper figure, the flow chart. So you'll again select and identify parts, identify your operators, identify your inspection and measurement location and environment, determine, so this is what differs from the continuous data. You'll determine the standard. So what are the operators comparing for a pass fail? What is the master standard? What is a master standard for assigning a value, let's say 1 through 5 to a product? Step 5 then is determining inspection order and inspecting the parts with the operators. And 6 is as the study organizer, collecting and analyzing the data. So this is just a quick example of an attribute agreement study. So just paraphrasing the bullets on the left there. So there's a facility conducting an inspection that involves comparing a product X-ray image to a master template. And based on the comparison, the inspector will assign a pass or fail value, which makes this a discrete measurement system analysis. So there are 15 parts selected, 11 were conforming and 4 were non-conforming to help determine if operators could tell that good parts were good and bad parts are bad. And an expert assessor created a master inspection result for each sample. And that is what was used for the standard column and the figure on the right, on the table on the right. And during the study, 3 appraisers assessed all the parts 2 times each, and the results were compared to the master results. To not bore you with the background details, this first bullet is describing that only 60% of the time the assessor agreed with the master assessment. So based on that percentage, the team decided, hey, if we're only matching between the operators 60% of the time to the master, we don't think that that's giving us confidence in us dispositioning our product. So they put in a corrective action to make the inspection work instructions and the template a little more robust. And based on that, we have the below results. And I guess I'll show point you to the bottom right here, or sorry, the center of the page, but on the bottom, the each appraiser versus standard, the assessment agreement. So as you can see, appraisers 1, 2, and 3, they matched 86%, 86%, and 100% of the time. So we had an increase across the board in the matching to the master. So this is just one example of you have a poor result coming out of an MSA study. You get with the team, you have corrective actions, you rerun the study and get an improved result. All right, so just to recap from the course objectives here. So a measurement system is the set of hardware, software, environmental conditions, the work instructions used, the people, and the objects that are used to measure and inspect to get your final measurement. So a measurement system is not just the gauge, which is a very common misconception. The goal of an MSA is to understand and quantify the sources of measurement system variation and define or help define where that may be coming from. The third takeaway is without an acceptable MSA to validate the measurement system, you could be making the wrong conclusion about your product or process or whatever you are measuring with the measurement system. So, right, that could be passing product that is actually out of specification or rejecting product that is actually within specification and could go to the customer. So understanding that variation in your MSA system will give you confidence in those measurements and the actions taken on them. Bullet 4 here is kind of describing what we went through with the discrete example. So when you perform an MSA and you do see excessive variation in the measurement system, you can take action on that to reduce the variation in the measurement system. And then once you have that validated, you can reduce variation in your process and products and make the correct decisions. And then bullet 5 here, I've kind of covered in the other 4 bullets. So to control a process using statistical methods, your measurement system must be evaluated and determine that the level of variation is acceptable and that measurement system is reliable then. So again, we went over what type of MSA you need to perform based on the type of data. So whether it's continuous or discrete, and then the different studies that entail after that, depending on what your measurement system looks like and what you're measuring. And then this bottom left bullet, so MSA, process, continuous. So remember to always plan your study out. There's plenty of resources out there that describe what the full plan should look like and what should be considered. Also for continuous data, conducting the resolution or accuracy ratio study, then your bias study, then your type 1 gauge R&R, which is only looking at the one operator, one part, multiple times variation, and then your gauge R&R, which is getting into your repeatability and reproducibility. So multiple operators, multiple parts. And then the MSA process for discrete. So again, planning out your MSA study, completing your attribute agreement study, and making sure that you have a calibrated master standard as well. Next slide. All right, so I think we can actually skip over this slide. It was 100% yes last time, so we can go to the next one. And then this was also 100% last time, so we'll keep moving. And then remember, the key takeaway here is gauge R&R and MSA are not the same thing. A gauge R&R is a type of MSA. It is not the only measurement system analysis that should be used. Looking at the bias study, the accuracy ratio study, the linearity studies, those are all a part of the full measurement system analysis. All right, so here are the planned activities in the future here. So some future webinars, maybe looking at some more in-depth variable gauge R&R results and how to conduct some computer-driven measurement systems, more in-depth on that MSA. And if there's any other topics that any of you would like to learn about, please shoot us a note and we can add that to the upcoming webinars. We use your feedback to help create updates to these documents. All right, and with that, we can start our Q&A session. Marnie, can you run this?
Absolutely, and I saw Andrea had her hand up, so
Yep.
We'll start with her.
Sorry, I didn't know the thing was to chat. Quick question. AS 13100 doesn't list an acceptable criteria for a attribute study for a minor characteristic. Does that just mean that MSA is not required for a minor characteristic for attribute data?
So, yes. It is being revised. We are looking at an AS 13100 update next year, and that is one of the things that will be fixed. There will be a requirement. It's just we don't mandate the MSA on the minor, so I think that's why it got left out before. The plan is it will be in the next version when it comes out, probably we're hoping middle of next year.
Okay, thanks.
No problem. Bill and Deb, I think, is listed here in the chat, and you did ask them a little earlier and we didn't see them. Slide 23 We want to go back to that one. There was a question on that. So the question here was, the left graphic, is that accurate? And then the right one, precise. And then the next question for Bill and Deb was, is the best outcome never calling a bad part good?
That's one of them. The other one would be don't scrap a good part, right? So it's both ends. What is the worst one? Yeah, probably pass a bad part, but MSA is going to help us do both ends, hopefully right.
All right, and then I think it was John and then Sergey. So John asked, can you please at some point comment on or provide some guidance regarding the use of read-across MSAs in AS 13100 or RM 13003? Oh, sorry, AS 13003. So John, AS 13003 is no longer an acceptable standard for aerospace engines since we released AS 13100. So the AS 1303 has been, I think, Becky, correct me if I'm wrong, archived, but is not actually for the engine's business. So it would be in RM 13003, we'd be making updates. And I think that is, if it's not on our list of things to look at for the next release, well, it won't be on the next release, but next year's releases, we can make sure that we give advice on that. All right, Sergey, I think you were next up.
Yeah, thank you, Marnie. My question is more about how to convince, like I get this all the time with CMM people, where they don't want to perform a full gauge R&R. They always claim that their machine is good and it was already calibrated. Why do they have to do the full gauge R&R? So they always want to do like partial gauge R&R. I don't know, just
Smart. I can help with that one, Marnie.
Oh,
Yep.
okay.
Yeah,
so
the flow chart would be good to show, or Becky, can you go up about 3 slides? There's a flow chart kind of thing. Maybe it's a little farther back. There, right here. So this is probably the right slide to look at while answering that question. Go ahead, Justin.
Yeah, so right, the CMM is just the tool portion of it, right? From a variation standpoint, you still have the environment, you have the part setup, whether it's in a holding fixture or a free state. You have the potential for different CMM operators programming different attack angles with the probe or using different probes that may affect the measurement itself as well and throw in some variation. But yeah, typically, right, a CMM is about as resolute as you can get with a measurement system in our industry. I don't think there's anything out there. It's basically used as, it can go down to like 10 digits, right? Where it's not even really helpful data at that point. But yeah, you need to be looking at the entire system, not just the gauge itself.
So I'm also going to refer to one thing I'm going to add to that, Justin. So there is an alternative to the traditional gauge R&R, which we call computer-driven measurement systems. And GE has underutilized that methodology, but it is something we are trying to drive and strengthen our muscle on how to do those, Sergey.
Yeah, that's what I was wondering about. I was looking at this because we use blue light, we use white light, we use CMM. And anytime I try to do some kind of study with those people, I get like 100,000 questions or rebukes as to why they don't want to do this. And I was wondering, like, from the specification, can I just hold them accountable to some kind of specification and tell them, I don't care, you have to do it by this spec, and there is no document for me to use to tell them that, because they always then say, oh yeah, we already done it once when we introduced this part back like 5 years ago. We don't have to redo it again because we haven't changed anything. Okay,
so it's gonna. I don't want to take us down too much of a GE path because we can have a side discussion, right?
Yeah.
Because there's 22 people on here, but from a GE perspective, we are flowing down a blue light spec probably next year. It matches and complements AS 13100 and will be for our supply base as well. So not just for GE, but all our suppliers. It is being worked on, and I am very familiar with it, making sure that it complements and doesn't contradict anything in AS 13100. So there are ways to do that, but I think maybe that's a side discussion that we have, Sergey. You can reach out afterwards, because that seems like a very specific question. We can guide you with what you're looking for on that.
Okay, thank you.
Okay.
Yeah.
And that's not just an issue at GE or in aerospace. I had
No.
the same issue in automotive as well in my 10 years in automotive. So
Absolutely.
you're not alone in the fight.
No. All right. So Kyle asked, with aerospace, is there a target number of parts to have to do a proper MSA? Is this much different than automotive with sample size? Anna, Justin, do either of you want to take that, or do you want me to take it?
I can take it. At least
Okay.
I can start, maybe. So in general, when you have a continuous MSA, the recommendation that we have is basically at least 10 parts, at least 2 operators, and 2 repetitions, right? In the case that you're doing a discrete MSA, like for example, an attribute agreement, then you need a little bit more parts. As I think we're recommending about 30 or more. And the idea is to have part of those should be non-conforming, and part, like about 3/4, or, well, yeah, 3/4 should be conforming, and at least 1/4 should be non-conforming to perform the discrete MSA. Is that different to the automotive? Probably Justin can answer that question better, since your
The
background in automotive.
recommendation, so on it, I want to point out your words though, was recommendation. It was not a requirement on the number of parts. So it is different than automotive, where they require 10 parts minimum. In aerospace, it's recommended for 10. The requirement is that we're putting out, requirement we're going to put in the next revision for RM 13003, which we're currently writing, is there has to be a minimum of 3.
Mhm.
Right. And then there's stuff around that as to why it is that small. But I think what came out in RM, and Justin, please, jump in on this one, right? One of the things that changed in RM 13003 is we moved away from the AIAG recommendations, and we moved to aerospace, understanding that we have a lot less parts to deal with, or a lot less parts available.
Yep, exactly. And as always, a lot as AS 9145 becomes more prevalent in aerospace, it's going to be in your contracts. Different customers, airframers, are going to come up with their own recommendations or requirements. So always work with them as well if you're not following the industry norm as required. But yeah, the automotive industry was 10 for continuous data, and some OEMs like Ford, I think it was 200 parts minimum for a discrete data. So it's very difficult to meet that, very time consuming.
Yeah.
But the first articles from Ford, also the first purchase order, because I was involved in a lot of those launches at Ford, also included that many parts in the first order minimum.
Right.
So,
so they were already produced.
Difference.
Yep,
yeah.
Exactly.
All right. So I think it's Adam next. I don't see any other hands up. Feel free to stick it in the chat or put your hand up. So Adam asks, how would the standard of acceptance affect the decision rule? For example, if the study was accepted at 10% of the total tolerance, and then a part measures 99% of the tolerance, there is a possibility of passing a non-conforming product.
Morny, was that a topic for ARM 13003 where you potentially apply gauge variation to that measurement system, or the product spec to create bands?
I think there might be 2 ways we look at this. And part of it is because of the rewrite. We literally just rewrote some of this. We have put in the upcoming RM 13003 and a requirement that for the study, you have to cover 80% of the expected tolerance. So you're right. If you're at 99%, there's a possibility we didn't put it in our study. And And I know literally that was this week we were working on sections like that as to how to diagnose it. And I know I missed some of those meetings, but we did talk about how we want to contain 80% of the process variation that we have or is expected in the MSA study, even in small sample size. We want to have a large amount of the variation, but we don't necessarily cover all 99%. So you're correct. There is a possibility of passing off a non-conformance. Highly unlikely if your Gage R&R was at 10% acceptance and you had 80% of your tolerance range covered in your sample size. But when you got to like the 30% Gage R&R, you have a higher chance of that. Adam, did I answer that question for you? Okay, thanks, Adam. All right, I'll move on to the next question. Adam has a slightly different question on that. I misinterpreted it, so he's going to rewrite it. So Nada has asked, MSA is required for equipment used or each characteristic. Anna, Justin, either of you want to take that one to start?
For each characteristic. Okay, when you do the MSA, it should be every characteristic because it might happen that the equipment that you're using might be good for a characteristics and not so good for another one, right? So you do that for all of them. One thing I want to mention about the question before also is that depending on the analysis of the data that you use, if you use ANOVA or you use the XBAR, your 10%, if you're using the XBAR, might be a little bit lower, lower than it is in the than the ANOVA. Okay.
And I think like a really simple example to help with doing an MSA per characteristic is if you use a set of calipers or micrometer to measure the length of a square block, right? That's going to be pretty repeatable, should be reproducible. But if you try to measure the diameter of a sphere, right, you're going to have more variation on that. So it may not be the best gauge. And that's why you have to consider the MSA for each characteristic.
All right, Nada, does that help answer that question? All right, we have one from Harry. It's a long one, so just give me a second to read it. So further to Sergey's question, I think Sergey was saying that he has people ask if CDMS should be subject to full Gage R&R studies. My understanding was that the CDMS row in table 4 of AS 13100 is essentially a reduced Gage R&R study specifically to CDMS and is absolutely a requirement that must be met. Agreed. Yes, you ask, am I correct? Yes, you are, right? If the quality specification you're following is AS 13100, that is a requirement when the contract calls out AS 13100. And then you have to meet it as it's written in table 4. So Sergey asked if he could point people to a hard requirement for Gage R&R for CDMS, and could he not point people? Yes, absolutely. Part of the reason, Harry, I was recommending a side conversation with Sergey. I know he works at GE Aerospace, and we have multiple specs at play. So I just want to make sure that I understand which, if they are supply base that follow AS 13100 versus they follow another quality spec that we have, and in which case I would point him to a different document. That's why I was suggesting an
understood. Thank you very much.
Okay. But yes, absolutely. AS 13100 is definitely the place to point to. All right. Okay. Adam, I'm going to come back to yours. I'm going to go to Nada's first, because it relates to the question that they had asked just before I repeated Harry's, which was MSA requirements for equipment or character-wise, and we did answer that. So similar character found in multiple drawings. Do we redo all the drawings, or similar characters can we do in a common MSA? So I can take this one. So Nada, if it meets the requirements laid out through, I don't think it's written in AS 13100, but it is laid out pretty sure in 13,003, and we are trying to clarify it in the upcoming RMDAR 13,003. If we can use the part family requirement, then yes, you can kind of group them together. So if you've got a hole that is drilled and the base material is the same, so the reaction between the drill that says drilling it or the mill that's drilling the holes and the base material, the reaction would be the same, then those could be grouped together. Where let's say they all have a 1 thou tolerance, you could group holes like that together in an MSA study. So you don't necessarily have to do every characteristic on every drawing when they are following the requirements of part family. What we do request is that in the MSA templates that we have and summaries that you should fill out is mark that you're doing it through part family, similar, comparison, and this is why it fits that one. Does that make sense? So if you have similar characteristics, yes, you can do it on a common MSA, but there are very specific requirements of what defines the part family. Does that help, Nada?
Yeah, yes, understood.
Okay, thank you. All right, so we're gonna go to Adam, and I think, Anna, this might be a good one for you because you were adding stuff in when we finish. So if we have a study that has been completed, passed, and we judge that the gauge was acceptable and utilize 10% of the tolerance, and then we begin using the gauge within inspection, a number of the parts later, an operator highlights that a part physically measures at 99% of the tolerance. Would this part pass or fail? Or in theory, should the total variation in the MSA study be removed from the tolerance so that a non-conforming part could never be incorrectly deemed as acceptable? Do you want to take that one, Anna, or do you want me to start it?
Yeah, why don't you start with that one?
Okay. I'm going to start with your last bit first. You absolutely have written a best practice that if we have the ability to take out the MSA variation from our tolerance, right? We're not going to change our drawing tolerance, but let's say we build an internal tolerance that has removed the MSA variation, i.e. the 10%, then yes, you can get into a situation where you are, I won't say guaranteeing 100%, but you're guaranteeing at a higher than 95% confidence that you're not going to pass a non-conforming part.
Non-conforming part, yeah.
I would take the part above that you asked, the number of parts later you found one at 99% of the total tolerance. That part, because of the gauge, might end up passing or failing because you have that 10% known variation in the tolerance. If that part is actually, at 99% of the tolerance, it could measure as out a non-conformance, or it could measure as conforming. We're in that band where it's questionable as to whether it would measure as good or bad. Let's assume that you measured it and it passed, then you would ship that part. Now, what happens after that, when it got to the next piece in the supply chain and it didn't fit, then you'd probably end up in a non-conformance situation on that part, right? Because if someone else down the stream marked it as non-conforming, that initiates an investigation. And then at that point, one of the clauses in Table 3 is in an escape situation, we reassess our MSAs. So you may be in a situation where you're reassessing your MSA. Does that make sense? Because you're in that gray zone of, well, it's at 99% of the tolerance. Is it actually good or is it actually bad? We don't know with 100% certainty. If you took out the MSA variation out of your tolerance and had internal ones, then you would know that 99 you would end up, probably reworking it, would be your internal policy. Did I answer your question, Adam? So best practice, absolutely, to take that variation out. It is not always possible. It is currently not embedded into the standard if your MSA is passing, but it is a recommendation of best practice. And I think You'll see a dramatic change in the upcoming RM 13003 when we release it, and we figure it's going to be about mid next year. We have reorganized the content a lot to sort of flow through different scenarios. So I don't know where we might put this example yet of what to do. It may be in the disposition chapter, but we've kind of reorganized to really basics of MSA, definitions, and then there's a whole chapter on planning, and then we've got continuous data MSA analysis and response, and then the same with discrete, and then there'll be a dispositioning chapter. And then some of the more complex or advanced statistics will get released later in the year in a similar flow. We'll re-release everything from RM 13003 early. It just may not all look the same. Okay, any other questions? And thank you all for hanging in, because we have definitely went over time here. But awesome questions. All right, so summary. This was recorded. The video will go up on the website in a few days. We did a great job on the Q&As. I thought this was great. Thank you so much for all your questions. Feel free to, once this goes onto the website, you'll get an email with a link on where to find it. So feel free to share it with other people. It is great that we archive these so they can be used. If like an hour from now you think, I wish I had have asked, there is a way through the AESQ website to send in questions to the committee, and we will address them later through the website. All right, is there anything else? I think there's just a thank you, Becky, in the next one. Yeah, thank you so much for participating. We appreciate the great questions and interaction. This was awesome.
Yeah, thank you very much.
So have a great day or evening.
Bye.
Thanks.
Bye.
Bye.